Thank you, Samuel. And thanks to the organizers very much for inviting me to this wonderful conference. I was told the microphone's amplifying. Can everyone hear? Okay? All right. So I took Jean-René's requests quite literally in the sense that I'm mostly surveying other people's work and only going to touch very briefly on a couple of my results. And also I took his request to use the superb boards at CERM quite literally. But I do want to check because I was sitting in the back. It was quite hard for me to see sometimes. So for instance, if we write at this size, are the people in the back able to see? Or if you want to sleep, you can sleep. But if you want to read, I want you to be able to do so. All right. So the topics I'm going to talk about are quite similar to what Shmuel talked about in his last talk. And so thanks to him for defining some of the things so that I don't have to. So the general question I kind of want to address is what can be said about computability of, here I do have to apologize. I believe in my abstract I said something about entropy and pressure. The things I'm going to talk about are technical enough that I really want to just stick to entropy today, but I promise that everything I'm going to describe kind of follows for pressure as well, and if you're particularly interested in the pressure case and wish to ask for some clarifications or details, ask, and I may oblige or may refuse. We'll see. But for most of the definitions, I plan to talk about entropy today. And I promise I'll say what I mean by computability because I know this has been different in different talks. So let's start. Probably this part of the talk will only be 3 minutes long because I'm essentially just going to say, based on what Shmuel said, everything is great in d equals 1. But on the off chance someone wasn't at his talk or something, let me just briefly mention something here. Oh, and I'm so sorry. When I say computability of entropy, let's say for shifts of finite type. Of course, there's no hope of saying something about entropy for all subshifts because you could see every possible number as the entropy of a subshift. And I left a gap here because, as Shmuel pointed out, every shift of finite type is conjugate to a nearest neighbor shift of finite type. And so just for simplicity, I'd like to reduce to that case because it's equivalent to the general case. Okay? So just to give a couple, I know he defined all of these things, but again, in case anyone wasn't there, just to give a brief definition. So we'll say a ZD, hereafter shift of finite type will be abbreviated by SFT, and maybe I say nearest neighbor SFT is defined by, the first component is a finite alphabet A. I put in parentheses here, nothing will be lost for the entire talk if you maybe just picture A's as being zeros and ones. That's pretty close to the general case. And then we also need some legal pairs of adjacent neighbors. And if it's not clear what I mean by that, I promise an example is forthcoming, which I think will clarify everything here. And so maybe we can even fit this example here. So an example is the so-called ZD hard square model. I think some talks may have referred to this as a lattice gas model when you add a potential. Again, I'm not going to be worrying about a potential right this moment. And this is quite simple. This is literally alphabet is 0, 1. And 1, 1 is forbidden in all cardinal directions. So in particular, for d equals 2, which is the case I'm going to talk about for most of this talk, you would say you cannot see 1, 1s horizontally, and you cannot see 1, 1s vertically. Okay? Is that definition clear? We're okay with what this model would be? All right, fair enough. So now let's do the 3-minute d equals 1 portion of the talk. D equals 1, oh, and we need another definition, sorry, which is topological entropy. So this has been spoken about again in several talks, but here I'm very thankful to Shmuel because everything I was going to say about topological entropy he already said. So perhaps I'll just sum up by giving the definition here. Let's say for all n let's let L sub n of x equals the number of patterns with shape an n cube appearing in points of x, which I'll just badly abbreviate by saying in x. So just as a very silly example, if we had the hard square model, we could say perhaps 1, 0, 0, 0 is in the to language of this model, because that's a perfectly legal word. It doesn't violate the only rule behind the hard square model, which is that you shouldn't have two ones next to each other. And now it's quite easy to define topological entropy. This is just the limit as n goes to infinity. Let me try not to make the common mistake of forgetting my d here. So we'll say 1 over n to the d times the log of the size of this n language of x. So Shmuel already explained this better than I could. Feketa's subadditivity lemma, this is a subadditive sequence, so you get convergence. You can even do this in general amenable groups, which I might talk about at the very end. But this quantity always exists, and it measures some very important quantities of your dynamical system here. And for future reference, I want to just note, it's also a consequence of Feketa's subadditivity lemma, of course, that this is an infimum as well, meaning that every one of the terms in this is an upper bound for h of x. Okay? No questions here? Okay, cool. So now we can actually make sense of the question above. We want to sort of know how well we can approximate this number in general. And here's the promised extremely uninteresting d equals 1. Sorry, the d equals 1 case is very interesting. Here's the uninteresting thing I have to say about d equals 1 for this particular question. H of x is always log of lambda for some lambda which is an algebraic number, which is clearly computable from the adjacency rules. I'm not going to go into this because it's extremely classical. And so in particular, lambda is a computable number in all cases. And it's even computable very efficiently, which I'll comment on perhaps in a couple of minutes. So I don't have much to say about d equals 1. For most of this talk, I'd like to say what happens for d equals 2. And so maybe let's put some of that over here. Actually, no, I take it back. Let's do it here. So what about d equals 2? Okay, so even though I know a lot of people in the audience are experts on this, let me just start with this classical amazing result of Hochman and Meyerowicz. Who proved that alpha, a non-negative real, is the entropy of a Z2 nearest neighbor SFT if and only if alpha is, I believe they use this term right recursively enumerable. Just for this audience, maybe I'm going to phrase it slightly differently. I'll say computable from above. And again, I know many people in this audience are much more experts on computability theory than me, but at the risk of saying something obvious, I'll say computable from above just means there exists. I usually say algorithm. If you want to be really classical, you could say a Turing machine, you could say a Python program, I don't know, something like this. There exists an algorithm which generates a sequence of approximations Pn over Qn such that Pn over Qn converges to alpha from above, right? And this result, of course, could be the topic of an entire course, so it's not my place here to really comment on all of the implications of this, but I want to focus on one very small implication. Not every computable from above number is computable at all. So one, very interesting corollary of this is entropies of a Z2 nearest neighbor SFT need not even be computable. I'll put 3 exclamation points to illustrate my incredulity at this really cool statement, right? So you can take a completely computable set of Wang, you can take a very explicit set of Wang tiles, and yet it may be the case that the entropy that you make out of that is not even a number that you can compute to arbitrary precision. Okay, so I want to pivot a little bit. This isn't really what I want to talk about. This is just to set some context. What I want to talk about is, as Shmuel pointed out in his talk, much of the time for sort of nice systems we want to work with, you are computable. And not only are you computable, you're computable efficiently. And so what I want to talk about today are sort of some classical results and arguments that imply computability. So what types of conditions could give you that? So I will mention one positive result, just so we're not too depressed by this. However, for X, the hard square model, not only is h of x computable, it's computable within a precision n inverse in polynomially many steps, which I will informally refer to as polynomially computable. So this is good news. We shouldn't just say systems don't have computable entropies. For ones that we want to study, often it's the case that particular properties they have tell you something good about this. This was independently proved by Gamernick and Katz. And myself, using completely different arguments. And what I'm hoping to do later is at least roughly outline the Gamernick-Katz argument, because to be honest, I think it's much easier to describe quickly. Okay, so for the rest of the talk, I kind of want to focus on what is it about the hard square model. And I mean, not just the hard square model, these will be general hypotheses, but what are things about the hard square model that might cause you to think that it has good computability? I should point out it satisfies Shmuel's conditions. It has, he only needs d-1 symmetric directions. In this case, every direction symmetric. So already you get some computability from that. But since I didn't practice how to tell you runtime of that, I'm not going to comment on that further. Let me comment on a different property it has. So for the first portion of the talk, I want to focus on what I would call topological mixing properties. I guess properties is not accurate because I'm going to tell you about one, but there are lots of topological mixing properties one could discuss. And so here's a property called, so let's make definition. We'll say X is strongly irreducible which we'll abbreviate SI, so I can have as many acronyms on the board at once as possible. So X is strongly irreducible if there exists a gap, which perhaps I'll call G, such that if U and V are in the language of X, and they're separated by a gap of at least G, then you can complete to a full point of X. I'm aware this isn't incredibly formal. That's because I would vastly prefer you understand the definition via the picture I'm about to draw rather than this sentence here. So the picture is essentially you take any pattern U, any pattern V, make sure that they're separated by at least G. I do not care which metric you use, as long as it's equivalent, and then it just changes what the distance G would have to be. And as long as these two are legal patterns in the sense that they actually individually appear in some points of your shift of finite type, there's some way to fill the intervening space to get an entire legal point of your shift of finite type. So as perhaps the world's silliest example, the hard square is SI with G equals 1. Why is that? Because if I give you any two patterns whatsoever and they're legal, it's always scary to ask audience questions, but what do you think we could flood the rest of the plane with and get something legal? At the edge of hearing, yeah, zeros, right? So this is fairly straightforward. So this is SI at G equals 1 because you can fill the rest of the space with zeros, because the only illegal thing is two ones, so you can't possibly have created anything illegal. So briefly, I want to mention that just this topological mixing property alone is actually enough to get computability in D equals 2. I won't give you every step, but I at least want to just show you where this comes from. The bad news, just to warn you in advance, is going to be that it's not going to give us a very good rate of precision. In particular, it's not going to get us all the way to this magical polynomial computability that I referenced. But we can at least see how some of these arguments could work. Whoop. Yes?
In the algorithm, is G an input, or can G be just the existing G?
Is your question that if you know SI but you don't know the gap, does that still give you? That's an excellent question. I think in this case it's going to end up moot because I'm going to cheat and say that I want our language to be decidable. I promise I'll say what I mean by that in a minute. And then I think you could figure out the G immediately. But if you want a real answer, my suspicion is that you don't need to know the G, but I'll be honest and say I do not immediately know the runtime bounds if you don't know it. I will pretend you know it, I suppose, is the answer. All right, so in fact, I'll just kind of mention this. So theorem SI for D equals 2, in fact implies computability of h of x in exponential time. So nowhere near what we're hoping for, but it's a starting point that we can work with. So how does this argument work? So why? Well, perhaps it's good before I try to give this proof to at least just give the vaguest sense of why we even know computability from above. Oh, yeah. Where is it here? Yeah, so just the same way I said polynomial computability on the top board. I suppose I didn't define exponential, but just replace the polynomial with an exponential. Correct, yeah. Maybe I should have even highlighted that more because I know sometimes it's to get the nth bit. So here, just because it's what will be easiest to describe, I'm just always saying to get within 1 over n, how many steps do you need? Is that good? Cool. Yeah, sure. Lower bounds, as far as I know, are impossible to come by. I mean, this is infuriating that for hard square, no one knows the rate of computability because it might be log of a rational number. I mean, it's not. Any computation time I say is only an upper bound. Because again, as far as I know, I guess Shmuel gave one of the only examples in the world where we know it's not log of a rational number, which would be domino, right? Or monomer dimer. But in general, again, I'm sure that the entropy of h of x is not log of 3/7, but as far as I'm aware, there is no proof of that. So lower bounds are, if you come up with a way to do that, I would love to know, but they're nearly impossible to come by. So thanks for clarifying. When we say polynomial, when we say exponential, all of these just mean there is a way to do that. Cool, any other questions? No, okay, so why is this true? Well, I just want to note, we talked about this fact that this limit is an infimum, so if we reinterpret that, we can say for all n, h of x is less than or equal to, and this wasn't an accident, I now am really in the d equals 2 case, which we will be for the remainder of the talk. So here you get an upper approximation for h of x. Some people in the audience are probably smirking because I'm not being nearly careful enough. There's no reason that this number is algorithmically computable at all. This essentially comes down to saying which words are in the language and globally admissible and which words aren't, and this is in general an undecidable problem. But I get to cheat. Part of Hochman and Meyerowitsch's wonderful proof is to say that SI in fact implies that there exists an algorithm to decide, really it's to decide if a word is in the language or not, but since it's all I need, I'm just going to say there's an algorithm that'll let you count how many n by n patterns there are. So this gives us our upper bound, and this is why we're computable from above, and so what we need is a lower bound. And in general, I'm not aware of too many lower bounds. The only cases I know of would be the symmetric conditions that Shmuel mentioned, and some of the things I'm going to mention today. But in the case where you're SI, there actually is a lower bound. Which is that if you take the number of n by n patterns, take the log, and rather than dividing by n squared, you divide by n plus g quantity squared, that already gives you a lower bound on entropy. And now we're in quite good shape, because here we have upper and lower bounds, which are, if you want to figure out how additively close they are, this is a mild annoyance with least common denominator, so I strongly suggest we think about the ratio instead. They have a ratio of, what, n plus g quantity squared over n squared, which converges to 1. So now we're in business. You basically can say, go until these two bounds are close to each other. It's quite easy to decide how far you have to go until this gets sufficiently close to 1, and then we're in good shape here. I was planning to prove this bound, but shockingly, it never happens during talks. I'm behind. So I think I'm not going to prove this bound because it's not anything incredibly illuminating. But I do at least want to comment on why I claim this gives you exponential time, because so far I've said nothing about the runtime of these algorithms at all. So here, let's say, how long does it take to generate the end language of X? Okay. And here, we're going to get sick of this phrase, I suppose. I'm going to cheat again in some sense in that Hokum-Najarovich's really clever argument here doesn't come with any sort of a runtime necessarily. For every example I'm going to comment on today, it's actually quite short to generate what the language is. For instance, picture the hard square. If a word looks legal in the sense that you have not yet violated the adjacency rules, it is legal. So let me just say that again in case I said it too fast. In theory, this could have a significant addition to the runtime. In practice, for everything I'm going to talk about today, it won't cause any addition to the runtime here. So if you want to know how long it takes to generate ln of x, I just want to mention something briefly here. The best guess, or perhaps I shouldn't say the best guess, but the most naive guess that I would have come up with would have been that it's something exponential in n squared, because you can take the incredibly useful algorithm of build every single word on the n by n pattern, see if they're legal or not, and then take the set that you obtained. It turns out, however, that there's a trick to reduce to e to the, sorry, these are all big O's, e to the big O of n. And I don't think I'm going to prove what this trick is, but I also feel worse than I thought I would, not even remotely alluding to what the trick is. So let me at least just try to say out loud. So the idea here is if you have an n by n pattern, and you want to try to count how many words there are, as Shmuel noted, there's a wonderful theory for one-dimensional shifts of finite type where counting patterns literally just comes from taking this adjacency matrix, and you can look at patterns, or you can look at legal adjacencies for that. So the trick here is we can view this as an n-letter word where your alphabet is now these entire n-high letters. So now we have kind of a nearest neighbor SFT going horizontally where this is our alphabet. And here's the part where I'm not going to bore you with how the sausage is made because I have other things to bore you with, but it's very easy, in fact, algorithmically to write the adjacency matrix for these n-high strips here. There's a very simple substitutive argument that you can set a computer to do quite quickly. So as a horrible explanation, I'll just say this trick is to view your Z2 pattern as a one-dimensional pattern. I will point out, just in case people want to think about higher dimensions, that to the best of my knowledge, this trick only works to reduce one dimension. In other words, if you wanted to work in z equals 3, please let me not give the impression you can count the number of patterns in e to the little o of n. It'll be e to the little o of n squared. So you can always cheat to get one fewer dimension than you think. Okay, so this is a little brief, but that's because what I mostly want to focus on is how topological conditions alone, at least in my experience, although people know other theorems, I'd love to know it, they don't get you further than this. I know of no theorem at all that kind of just says because you can mix between patterns efficiently, you can get down to polynomial time. You basically are stuck at this sort of bound, and in fact, when d is greater than 2, it's even worse. It's not even quite exponential time. I think it's like e to the n squared roughly, or something like this. So with my remaining time, I want to focus on what is it that's so great that will give us kind of better or more useful bounds here. All right, let's bring the top board down. Okay, I can't do two at once.
But can't you just count this using dynamic programming by cutting in half?
If I knew what dynamic programming was, I could probably do that. So possibly, yes, I'm sorry, I'm not a, I trust you. If you say you can, then I believe. But are you saying in higher dimensions you can even do better, or? No. Okay, so it's probably these are two ways of saying the same thing, and mine is just more naive, but very likely this is possible. Okay, so eraser. So what is the sort of magical type of property that I keep alluding to that will get us these better results? All right, so they're measure theoretic properties. Okay, so what do I mean by measures? Well, in a normal room, I would spend 5 minutes saying, what do measures have to do with that? You know the variational principle, so I'll get to the point. So the idea here is that we can get at this topological entropy because of the variational principle. And of course, there's a general version for general dynamical systems, but since we're expansive, I'm just going to skip to the good part. We have a measure which actually achieves the full topological entropy. So there exists a measure of maximal entropy mu such that h of mu is actually h of x. Right? So fine, not very useful so far. And also I should at least say what h of mu is. So let me see if we could put that on this board. So what is the entropy of a measure mu? This is the limit as n goes to infinity of 1 over n. And now instead of talking about the count of the number of n by n patterns, I'm going to talk about a quantity called h sub n of mu. What is h sub n of mu? I think this has shown up in a few talks. This is just the sum over all possible words in the language of your SFT of minus mu of the word times log of mu of the word. Okay. 2 comments here. I really should be putting square brackets around everything to illustrate that these are cylinder sets, but I got sick of that even in my notes, so you would have as well. So this will be my shorthand for saying mu of a cylinder set. And what does this really mean? This just means mu of the set of x such that x actually sees the pattern mu w at sort of the origin or at its shape. Oh, you want me, oh, n squared here, yeah. I was so proud I didn't put n to the d before, but then I forgot an exponent completely. Thank you. All right, so far you shouldn't be impressed. I've taken something simple, topological entropy, and written it as something complicated, which is measure theoretic entropy. So what's kind of the benefit here? How does this help? Well, how do we get at this measure mu? I mean, if I'm claiming this is useful for approximation purposes, then I'm going to need some way to say something about this mu at all. It is not necessarily unique. Although the only cases I'm going to talk about, except maybe the last 5 minutes, I will need uniqueness of it. So in general, this is useless. But if we have some kind of strong uniqueness properties, we'll be able to do something. But in general, no, I think it was maybe Rodrigo Bisico's talk where he talked about the Ising model, and you could get multiple measures. His were equilibrium states, but Ole Hagström recreated this, and Burton and Steiff as shifts of finite type. So absolutely, you could have many of these. It could be terrible. So you're right, perhaps my sentence here is implicitly saying there is only one, but how do you get at any of them, I guess, would be the idea. And the key is something I think Tom's going to talk about, which is this classical Lanford-Duell theorem. Although the version I'm going to mention technically is due to Burton and Steiff, who were kind of reproving a version of Lanford-Duell theorem. But what does it say in our case? It says, given an n and a boundary delta on the outer boundary of 1 over n squared and a w in the language of x, oops. And in fact, let's say 2 words in the language of x, such that w and w prime are legal given delta. Please see my comments earlier if you find the sentence confusing. There's a wonderful picture that will be much better than the entire sentence. But mu of w given delta is equal to mu of w prime given delta. So the picture I want us to visualize here is if I give you a box, and then I take some configuration, pattern, word, did I miss anything that people call these? So whatever word you prefer to use, take some delta there, and you take a W and a W prime, which both are legal for the SFT restrictions given this boundary delta, then actually they have to have exactly the same conditional probability. I, of course, can't prove Lanford-Durrell or even Burton-Stief's version for you, but I can cheat and maybe convince you that I've proved it. The idea is, suppose that you had some boundary in two words such that this one was 60% conditionally likely and this was 40%, then you should be able to do some sort of probabilistic process where you kind of tweak these probabilities to get closer to 50-50, and because that's closer to a uniform distribution, that should increase the entropy. Okay. Seeing more boredom than confusion there, so I'll assume that perhaps that's easy for everyone. This is not the version of Lanford-Durrell or Burton-Stief that I actually care about. So a corollary is that mu of W given delta is equal to 1 over the number of legal delta fillings. So in other words, if you give me a delta, and it can be fillable in 11 ways, well, all 11 of those ways have equal conditional probability by what we just said, so each one of them has conditional probability 1 over 11. So it's kind of wonderful in that this measure itself, in terms of its actual values on words, may be bad to work with, it may be non-computable, it may be computable but difficult to get a hold of. These are rational. Those are rational numbers. Every single conditional probability you want to look at of this sort is like 1/11th or something like this. So this sounds useful, and we just need to figure out how to sort of leverage it in the way that we want. And I, in fact, want another corollary of this, which I think we can fit on this board. So even if W is on a smaller shape, then, all right, before I tell you what this is, let's draw a picture so that maybe we can all discover it together and I don't feel like I'm saying this too quickly. Let's say we've got our boundary delta, and I take a smaller word W inside. So now there's a gap. It's not taking up the entire shape. Well, given delta and given W, there are some ways of filling in this intervening space, and they all are equally likely given delta by Lanford-Durrell theorem. So that means we're going to have a similar ratio here. It's just that on the bottom, we're going to have the number of legal delta fillings. And on the top, we're going to have the number of, allow me to coin this term without defining it because I think it's evocative, the number of legal ways to fill the intervening space between W and delta. Still rational, still computable in roughly singly exponential time. So the big picture of all of this is that even if we don't have exact information about mu, I do have exact information about every single one of these conditional probabilities. And in theory, perhaps that could be helpful for us for doing something or another. All right. Yeah? Sorry, I said the time it takes to count those fillings should be singly exponential by the same. You're right, it's more complicated, but it's by the same trick we did before. You generate all of the fillings. Actually, you generate the entire N language in exponential time. Then you just do a quick check for which of those are legal given delta and which of those are given W. And you look unhappy, which means I'm not being careful enough about something. But it is true that it's perhaps slightly more subtle, but you can still generate this quickly enough. All right. Yeah, so for finite range potentials, I mean, nothing changes from what I've said on the board. For infinite range, you need some sort of maybe oracle that tells you a good locally constant approximation at step n. And then at the risk of saying something silly, of course, I'm not going to say that for every potential you get the same rate of computability because some potentials are badly non-computable themselves. So it should sort of be, once you give me an oracle that will let me call the approximations to the potential that I want, we should still be able to do most of this. Although I still haven't said exactly what this is. So far, we're not good enough to do anything yet. But so I might come back to your question once I say something more carefully here. So let me erase this. Sorry, I'm listening. Sorry, I was erasing and listening. Oh, before you erase. Okay, that needed to be louder. Sorry, that's my fault. Too late, but go on.
So there are deeper notions of tuples with missing than SI.
Yes. How much do you need SI itself? Very little. Okay, so there are two kind of answers to your question. One weakening is that you can do this version that's just on rectangular blocks. I think Mike and Michael Schrodner and I call this block gluing. For d equals 2, everything still works in that case. For d equals 3, it's not known whether that even implies computability by itself. An even better question is, what if you don't require the gap to be uniform, you require it to, or you allow it to grow slowly with the size of the blocks you're mixing? This is really cool work of Benjamin Elouin and Sylvain Gangloff, and I'll let you ask Benjamin if you want to know their results. I think as long as the gap grows very slowly in comparison to n, you're still able to get some computability. And even though I can't quote the result, they have a really cool sharp threshold where it's kind of, if the gap distance has a certain property, you get nice computability properties. And as soon as you pass that, you could again see sort of any crazy non-computable number. Okay, so how to use this. And just to make sure we don't lose the plot entirely, I want to use this Lanford-Ruel to approximate measure theoretic entropy, because that will let me get the topological entropy by the theorem that they're equal to each other. So how to use this to approximate, oops. So as our game plan here, I need to approximate measures of words so that I can then plug those into that formula to approximate h of mu. And by itself, there's nothing I can do, because we have this kind of issue here, which is, and I think I have to not say too much, if there are multiple measures of maximal entropy, then unfortunately these conditional probabilities of W given delta could vary a lot over delta. I don't have time to go back and define the Ising model, but there was a very nice proof, I think, again, by Rodrigo about this Peierls argument, where you can have a phase transition and multiple MMEs for Ising model or associated SFTs, and then different deltas will give you different probabilities even as they recede to infinity. So we need to make some sort of assumption here. So there's a nice assumption called weak spatial mixing. Acronym number 4, I believe, so we'll call this WSM. And what WSM says is if delta and delta prime are both a large distance, let's say n, from W, then the conditional measure of W given delta and the conditional measure of W given delta prime are close to each other. In fact, I guess you want a constant times a negative exponential in the distance times an annoying error term that I'm not going to comment on further. It's so easy to make this mistake and avoid this, but in fact, you have to have some linear growth in this smaller pattern W. Otherwise, this condition turns out to be kind of moot. I think it implies Bernoulli, in fact, or something like this. Please. Two different boundaries that could be on W. So the idea is now, I don't mean to make this change too quickly. Before I was putting two different words inside the same boundary W. Now I'm putting the same word W inside two different boundaries, delta and delta prime. And what we're saying is as long as they're far enough away, they exert very little influence on what's going on near the center. This is very, very close to uniqueness. It's actually just mildly stronger than uniqueness. Or I guess I should be more careful. This is equivalent to uniqueness of the sort of uniform Markov random field with these conditional probabilities, but it doesn't have anything to do with shift invariance. It's actually possible that this could be non-unique and you could still have a unique shift invariant MME.
Even the short range?
What's that?
Even in the short range?
Even for phi equals 0. Yeah, it's upsetting. But what's that? I'm sorry, go ahead. That's a great question. For everything I'm going to do today, there will be. For this definition, no. So in fact, maybe it would be better to lean on my inaccurate picture and put them slightly more in the corner here, right? So all you're basically saying is boundaries have exponentially decaying effect on what goes on inside. All right, so why is this useful? I think I can fit one more thing here. So here's kind of a trivial fact, but it's actually a useful one, which is we can write the measure of any word using just basic conditional probability as a weighted average over all possible delta boundaries, even very far away ones. So silly statement, if all of these are very close to each other, then they're also very close to that. And so that means the version of weak spatial mixing that's actually useful for approximation, and its equivalent, is that I'm just going to say they're all close to the measure of W itself. Sorry to do that too quickly. I'm not trying to cheat here, but this is an equivalent definition to what we wrote before. And now, since this isn't even the good part I want to get to, I think I might just stop this portion and say, now this does something. And perhaps I'll just say what the something is out loud. And I'm not excited about it because it's still the bad bound that's exponential, just to warn you about this. So, but now what would our game plan be? Our game plan would be you take any word W, you take some boundaries that are very far away, you plug in every single one of these boundaries delta, and then you find the max and min of this quantity. They're pretty close to each other, so they're upper bounds on mu of W. Now you have good upper and lower bounds for every term in this series, which means you have good upper and lower bounds for this quantity itself. And sorry for doing so much of this out loud, but I want to save the board for the one nice proof at the end here. This actually sounds good, and in fact, if I wrote down the runtime for you so far, I think you'd be excited, in the sense that all of this is going to be approximable to within 1 over n in polynomial time. So that sounds pretty great. Why is that? Because you're approximating to within an exponential quantity in a time that we already talked about is only singly exponential. So why is my tone so negative? Because you still have to worry about the rate of convergence here. And that rate of convergence is still proved. I don't know any argument that anyone's done to prove that it converges quickly. It converges slowly enough, just like in the strongly irreducible case, that unfortunately this entire business here, maybe I'll try to summarize in one horrible sentence here. So this does yield good or efficient approximation for hn of mu, but the rate of convergence to, I think I need to raise this board, to the actual entropy, h of mu might be poor. And so unfortunately, what's the big end game of all of this is that this still, as far as I know, only yields polynomially time, nope, exponential time approximations to topological entropy. Okay. All right, so let me try to give you some good news. So with the 15 minutes or maybe 16 minutes I have left, let me try to describe the one kind of simple condition I know of that's in the same spirit, this is the good news, that is used in both of the proofs implicitly of polynomial computability of the hard square, for instance. So let me erase this. And so our third and final category here will be something I want to call the sequential cavity method of Gammernick and Katz. I suppose I should be fair and say that this has also been used by other authors. Brian Marcus and myself used it in a paper, and I think Raimundo Briceño has proved a much better version of it for several papers as well. But I want to highlight that they were definitely the progenitors of this technique here. All right, so how does this work? So I want to make some large assumptions here to finally start using the full power of the hard square shift, or at least close to it. So we're going to make an assumption that we have a safe symbol 0. I think Shmuel used this, was it a friendly state? Is that the term? Okay, I like friendly state a lot more than safe. So a safe symbol 0 just means 0 is legal next to all letters in all directions. So I chose 0 on purpose because in the hard square model that I'd like you to be thinking about for the rest of the time, 0 is safe in that model because the only issue is having two 1s next to each other. And I'm going to make one other assumption, which is strong spatial mixing. I think it's actually the final acronym, I promise. So strong spatial mixing, it's very similar to the weak spatial mixing property that we wrote. I promise I'll try to write it formally, but I think the picture is better anyway, so let me just refer to this picture. Weak spatial mixing says if you have two words, if you have a word W, and you have two boundaries, and you have nothing nearby the word W, then the boundary exerts very little influence. Strong spatial mixing says, what if to this picture I add some word u, and instead of looking at mu of w, I look at mu of w conditioned on this u and this boundary. Still, you want to say they're close to each other. So in other words, I don't think I'll do a perfect job of getting this epiphany moment with how these two conditions differ, but the idea is weak spatial mixing is just about one word given a faraway boundary. Strong spatial mixing is about one word given a nearby word, which could be right next to it, and boundaries which are far away from both of them. So let me at least attempt to write that down. So strong spatial mixing says for all w and u and boundaries delta and delta prime of a distance n away, the conditional measure of w given u and delta is close to the conditional measure of w given u and delta prime. And again, I want to make the same simplification I did before. Just float it away. I can still reach it. So I want to make the same argument I did before. You can use a slightly less pleasant conditional averaging argument to say this is equivalent, to just saying that the conditional measure of w given u is not affected very much by a boundary that we put far away. Okay? Again, I don't have time. This could be a whole course in statistical physics techniques. That strong spatial mixing is ludicrously stronger than weak spatial mixing. It's really a much, much, much stronger property. And with my last few minutes here, I want to try to explain how it can be used to give you good approximations in this case. So how to use SSM to get more efficient approximation scheme.
And again, you can have multiple measures, or not?
No, sorry. And maybe I think I did not comment on this enough. All of these conditions imply uniqueness. I think I may have mentioned before. Weak spatial mixing is uniqueness of the Gibbs state, so it's even stronger than uniqueness of the shift invariant Gibbs state. And then strong spatial mixing is stronger still. So both of these are light years beyond simple uniqueness of the measure. But thank you for clarifying, because I probably did not say this clearly enough. All right, so the key is a really amazing formula. And even if I don't get time to prove it, I think just showing this formula is really fun. So as long as you have both of these assumptions, strong spatial mixing and a safe symbol, here's a crazy formula where if you haven't seen it, then perhaps it will be surprising. So minus the log of okay, so I have to define some terms there. So what this says is it's the negative log of the conditional measure that you see a 0 at the origin. That's what this 0 here represents. Perhaps a vector would make it easier to clarify that. Given or conditioned on the event that you see zeros on some mysterious set P, which I haven't told you what P is yet. P is the lexicographic past of the origin inside Z2. So the picture here would be, here's the origin. The lexicographic past is everything that's either below it with strictly negative y coordinate or to the left of it. Okay. So since I think I might have less time for proofs than I want to really focus on at least making sure we know what this statement means, because it's really cool. So what we're saying here is you take a single conditional probability. If nothing else I say makes sense, this is a convergent sequence that we don't have very good control on how fast it converges. That is one probability. If we can just approximate that number efficiently, then we're in good shape. And all it is you say flood this with zeros. Bless you. And you want to know how likely is it given that you get a 0 here. Okay? Any specific questions on what this says? Tom says no. He already knows this, though. So, all right, well, I'll leave it up while I erase. This is for anything which has a safe symbol 0 and this strong spatial mixing property. Yeah. And so I think I can at least vaguely describe why this is true. So y all right. Well, questioning my organization, but I guess I want to convince you of a fantastic formula by giving you a slightly less fantastic formula, and then we'll try to tie everything together. So here's a lemma. And my lemma is that okay, so let's see if what I wrote, actually, it's h of mu, but h of x is perhaps even easier to see. So what this says, it says if you take just a single large pattern of zeros, the probability or measure of that should decay, so kind of exponentially in its area. The exponential decay rate, what you get by taking minus log of it and dividing by n squared, is actually the entropy. And this is easy. We may even be able to prove this before the end of the talk, so I may try to do that in the next 2 minutes. So why would this be true? Maybe every line will just start with y from the previous line. So why is this true? Well, it's actually not hard to give some upper and lower bounds on what the measure of this large pattern is. And I think perhaps giving some insight into this is better than giving a formal proof of this formula over here. So let's say I draw a square of size n here, and I draw a boundary delta. For every single delta in the universe, what could I say about the conditional probability of filling the inside with all zeros? Well, I can tell you one thing. It's equal to 1 over the ratio, or 1 over the number of possible fillings of delta. And I can tell you another thing. Filling it with zeros is legal because 0 is a safe symbol. 0 never causes any problems whatsoever. So that means this is definitely bigger than or equal to 1 over the full size of the n language of x. Right? But if I know this for every single delta, then the measure of the word itself is a weighted average of things like this. And if I weighted average a bunch of quantities, they're individually greater than or equal to 1 over the language, then by God, the weighted average is greater than or equal to 1 over the language. So now we get a lower bound for this quantity, which is of the right asymptotic size. So now all I would need is an upper bound. And for that, let's do something silly. Now I'm going to change my picture and say, what if I specifically choose a boundary of all zeros here? I'm certainly allowed to do that. And I'm going to surreptitiously change my diagram so that n is the entire width there now. And then I could certainly say that mu of a word of all zeros is less than or equal to mu of, or actually, sorry, it's equal to mu of this boundary of all zeros, which perhaps I'll call delta 0, times all this formula is trying to say is you could decompose mu of the big block of zeros by doing mu of this boundary and then the probability of filling the interior with all zeros after that. But what is that? It's 1 over the number of legal fillings. What fillings can you put inside a boundary of zeros? All of them. And so basically what we get here is that this is less than or equal to 1 over the number of n minus 2 by n minus 2 patterns. Why n minus 2 by n minus 2? Because I started with an n pattern, I took this boundary of zeros, so the size on the inside is n minus 2. All right, so then what we get is we get upper and lower bounds, which are of the correct asymptotic growth rate, and so that's what gives us this lemma here. So that tells us that if you want to approximate h of x, it's sufficient to get the exponential decay rate of these measures here. And I know we're almost out of time, but there's only one idea I want to mention, and hopefully it'll tie things together and show you why we defined this weird SSM property, and then we'll wrap up. Perhaps since I don't need it, I can erase the left-hand board now. All right. And now there's only one more idea to the entire proof. And just to make sure we know what I'm even trying to explain, it's this starred formula over here. So why is star true? Okay. All right. So only one more proof type thing in the whole picture. So what I want to do is I want to take this probability here that I now have very roughly convinced you is related to entropy in some way, and I want to decompose it. So let's look at 0 to the 1 nd. So a n by n pattern of zeros. So the idea Gemernik and Katz had, which is quite brilliant, is to decompose this as a sequence of conditional probabilities. So perhaps I've got my zeros here, and over here let's just make a diagram of ordering the sites inside this, this square. So let's just order the sites. Here's V1, here's V2, here's V3, here's V4, V5, V6, V7, V8. And then we just continue filling in row by row by row. So I think here's the last even remotely formal statement I'll write down. Which is, if you want to look at the measure of so that's the event we're trying to look at, the event where you have zeros on this entire square. That supposedly controls, if you know the exponential decay rate of that, you're done. And we're just going to decompose that as a product of conditional probabilities. I promise I'll only write one more. Okay, so to say the probability that you see a 0 in the lower left corner, then the conditional probability you see a 0 next to that, etc. And I promise I'll finish in 1 minute because there's really only one other idea I want to mention, which is, or not even idea, just what's the idea of the proof. I have no idea what the first few terms of these are. None whatsoever. But let's look at a term near the middle. Suppose I want the conditional probability of seeing a 0 here, given that all of the previous steps were filled with zeros. Maybe it's the only time I want to use colored chalk here because it seemed hard to read. You know what that looks really, really, really close to if you're near the middle of the box? It looks really, really close to that conditional probability. And what's the formal sense in which it's really close? This is the conditional probability of this word W given this word U. And now what's the delta I'm going to impose, or the background that's far away? It's finishing this entire picture of the lexicographic past. That was a terrible proof, but I don't care if 59 minutes in is not the time for careful proofs. So let me just tie things together for what the big picture is. Most of the terms here are close to, perhaps we'll give this conditional probability a name. Let's call it rho. Most of the terms are close to rho. So what do I have? I have a product of n squared terms, most of which are close to rho. That means the product close to rho to the n squared. That means the exponential decay rate is essentially rho. And so that's how we can use that lemma to get this formula here. And I believe I have negative 1 minute, but just to say 30 seconds more or else the whole talk was wasted for you. It's arguable. Don't tell me if it was wasted. Anyway, where are we at now? Now we have this wonderful formula that you just need to approximate one conditional probability. There's no decay rate whatsoever. Even WSM techniques, weak spatial mixing, are enough to say, do approximations to this, take very, very far away boundaries delta. You can get exponentially close to this quantity with singly exponential time. And so this formula here, with steps we're not going to imply, or sorry, not going to finish, implies that this is polynomially computable. I'm not claiming this is the only technique in the literature that implies this, but most of them seem to be fairly similar. Okay, and that's it. Thanks very much. Yes.
I thought that. Wait a minute. This conditional probability.
Which additional? Conditional.
Probability in the last step. Mm-hmm. Why is it defined? I mean, conditional probabilities are generally almost everywhere.
Yeah, that's an excellent question, and one of 50 things I didn't say enough about. The 2-second answer is SSM. I mean, so you can literally say, what's the naive way you could interpret that conditional probability? You could interpret it by saying take larger and larger approximations to the lexicographic past, so take boxes. Typically, there's no reason for that sequence to converge, but in fact, it's a consequence of SSM that quantity is that sequence is exponentially Cauchy. And so in fact, if you want me to be really, really careful, that's even the interpretation in which it's easiest to give this proof here. That being said, it's also easy to prove that it coincides with the almost everywhere kind of conditional probability interpretation here. It is defined for every tail. Once you have SSM, you just say, here's the thing you want to take a lexicographic past here, and as you recede, the sort of additions that you're making are giving exponentially small influence. In fact, since you gave me an in, I'll just give one tiny plug, which is to say, the real version of this, which was pushed a little bit further by Brian and I and by a couple of other people, is not so much, my chalk, not so much to look at this quantity, but to actually say, and I promise I'll keep this short, but it's kind of cool. So this is actually a formula that's always true. People might have seen it in different guises here. This is just saying, if you want to get the entropy of a measure, by the way, if you hate this, if you've heard of entropy as the present condition on the past, congrats, you know this fact too. It's the same proof. So you can say that h of mu is the integral of minus log of what appears at the origin given what appears on the lexicographic past, d mu. A way to interpret Gammernick and Katz's statement is you could replace this d mu with the delta measure on the point of all zeros. I know that's a stupid way to write an integral, but you can say it. You could say that if you just say I'm only going to look at x's assigned according to the delta measure on the point of all zeros, you recover this formula. The real truth is that there's some interesting results under a large class of shift invariant measures nu for which you can actually say that this formula holds. And that's kind of maybe the best and most natural way to interpret the generality of this. And that's how you can push beyond safe symbols, how you can move to things like K colorings, etc. But I'll leave it there. All what? I said a class. I don't know. That is a class. Sorry, I don't remember our exact result. It's certainly not true for all nu just under strong spatial mixing. You need some topological mixing property. You need some basic hypotheses on this. There are some systems for which it's true for all nu. That is true. No, the mic would be better.
So maybe I missed it.
I probably didn't do it.
Did you say that safe symbol implies SSM for?
Oh God, no. No, if I even allude, no. So you give me a good chance to clarify. So no, in fact, I mean, even the models that Burton and Steiff used, which were analogs of the iceberg model, or not Ising model, you can have safe symbols and not have strong spatial mixing. You can have safe symbols and not even have a unique measure of maximal entropy, which was kind of what Burton and Steiff discovered that made people quite upset working in ZD. I should perhaps advertise for, I think Markley and Paul were already mentioned. Markley and Paul had this very nice result maybe 10 or 20 years before some of these other results. If you have a large proportion of safe symbols in your alphabet, which the proportion depends on D, but let's just say 90% or something like this in D equals 2, I think they needed 15/16 of the alphabet. But if most of the alphabet's comprised of safe symbols, then most points kind of look independent enough of the time that that you end up getting strong spatial mixing. But yes, I meant to list those as two different hypotheses that we were imposing, not implication.
And what is the role of this exponential upper bound?
The exponential upper bound would...
Something else, like
do you mean role as it pertains to approximation, or... or just in general?
No, I mean, instead of being exponential in n, being a cubic 1 over n cubic.
Yeah, so I mean, that's a good point that I should have said more about. You can define these properties, weak spatial mixing and strong spatial mixing, not requiring exponential upper bounds. You can just say you're weak spatial mixing or strong spatial mixing with a certain rate. That being said, every single proof I know of in the literature goes by percolation theory, and you get exponential anyway. So it's not really costing us very much to say this. If you had a model for which you could prove a spatial mixing property, with a weaker decay rate, it would just mean that the computation rates we're talking about here would get weaker, because you're never changing the fact that the time you need to compute the approximations is singly exponential in n. So whatever that rate is would give you different run times for your approximations.
Maybe we will stop there to leave some time, and we keep the question for the break.
Sure.
Okay.
Thanks.
Thanks.